In these days, the scaler and the Geiger counter are very familiar, but I would suggest that such apparatus isn't really the way to introduce the subject of radioactivity in schools. These present far too many inexplicable things all at once. In this film, I hope to suggest a different development, presenting the subject experimentally and avoiding too many dogmatic statements or instruments which the pupil cannot understand. Anyone teaching about radioactivity will already have introduced the concept of electric charge. The principles of the gold leaf electroscope will be familiar. Let's look at a model of the electroscope. The pupil will already understand that when a charge is deposited on the plate, the leaf will rise. If there is a flow of charge, the leaf will rise steadily. The greater the flow of charge, the more rapidly the leaf will rise. The use of the instrument as a current measuring device suggests itself. However, there's a serious limitation. When the leaf is almost at 90 degrees, it can rise no more. How convenient it would be if we introduced a counter-electrode like this. When there is a flow of charge, the leaf rises, discharges against the counter-electrode, and starts again. The greater the current, the more rapidly the leaf rises, the more frequent the discharges. You see, we've got a current measuring device, and the frequency of the discharges is a measure of the current. Let's look at it. This is a gold leaf electroscope built as a projection electroscope so that I can get an image of the gold leaf on the screen. I bring up a charged rod, the leaf rises. I take it away, the leaf falls. I now bring in the counter-electrode as we saw in the model. I bring up the rod, a current flows. I take it away, it flows in the opposite direction. But a gold leaf isn't very robust, and it's very much better if I replace it with a foil or fiber. This is a phosphor-bronze fiber. I now have the delicate current measuring device I promised you. This is another version of the instrument. The lamp casts an image on the screen here. This time we have a rather larger counter-electrode, and the foil is made of aluminium strip. You can see it rather better in this spare I have here. The aluminium strip is sprung by a very fine quartz fiber at this end. If I bring up the charged rod, the leaf rises. If I take it away, it falls. To show its current measuring properties, I place this metal base over the top of the electroscope. It's insulated from the central electrode. I connect the counter-electrode to the outside of the case. And this, in turn, I connect to the negative terminal of this power pack. Which, in turn, I earth. I now connect this metal base plate to the positive terminal of this power pack, connecting it through this 50 megohm resistor for safety purposes. I switch on, turn up the voltage, a current flows momentarily, and now stable conditions are reached. There's about 3,000 volts across here. To show the current measuring properties, I can take my handkerchief, which is a bad conductor, and place it across like this. And you see, we get a current flowing. It's a very sensitive current measuring device. If I strike a match, the match has ionized the air, and we're getting a current. A radioactive substance. That too produces a current. In other words, we introduce this radioactive substance as an ionizing agent. I can place it in the top of the electroscope like this. And if I now place the canister over the top, I've formed an ionization chamber. I'll use this voltmeter to find the characteristics of the ionization chamber. With no voltage, there's no current. Turn up the voltage, and now a current is flowing. To measure it, I'll find the time for, say, 30 discharges. With 420 volts, we have a time of 48.5 seconds. I must turn up the voltage there's an increase in the current, and the discharges are more frequent. In this way, I can take a series of readings. I've already plotted these readings. The frequency of the discharge, which is proportional to the ionization current, is plotted against the voltage. You'll see that the plot flattens out when the voltage is greater than about 1.5 kV. For that reason, from now on, I will always use a voltage in this range, as its value isn't critical. And now you can use this instrument for a whole series of experiments. You can compare the strengths of different sources inside the chamber. You can do absorption experiments. And these are very important as they provide evidence for different kinds of radiation, which for convenience we call alpha and beta radiation. Later experiments will produce evidence for a third kind of radiation, gamma radiation. To do these experiments, you place a thin foil over the source like that, and then hold it in place with this brass cap. If you take a series of readings of the current for different thicknesses of the absorber, you'll obtain a plot similar to this. And it's the discontinuity in this plot which provides your evidence for two kinds of radiation. We can also use this instrument to measure the range of the alpha particles, provided you've got an ionization chamber with a telescopic top. Let's look at a model of the ionization chamber. Radiation from the source will produce ions and we'll get a current. But the alpha particles, when they hit this, will not have used up all their energy. If I raise it, more ions are produced and the current is greater. But there'll come a stage when there's no further increase in the current, because this has moved beyond the range of the alpha particles. This distance would therefore give us that range. I've taken a series of readings using this ionization chamber. And I've plotted them like this. The ionization current plotted against the distance between the top of the source and the top of the ionization chamber. This particular distance here will give you the range of the alpha particles. And now I can use this point counter in connection with the electroscope to detect individual particles. If I apply a high potential between this fine point here and the outer container, so that we're just about to get a discharge, then if I bring up a very weak alpha source here, a single alpha particle produces sufficient ionization so that we get a discharge and a pulse on the electroscope. I can connect the point counter to the electroscope like this. The principle, however, is particularly clearly seen in this apparatus. I have a very fine wire between this grid and the base, and I connect it to this high potential from this power pack. Once again, we're on the point of discharge, and if I bring up a radioactive source, ionization is produced, and we're able to detect individual particles. And this emphasizes beautifully the random nature of the process. And having shown the spark counter and the point counter, we have virtually introduced the Geiger tube. And this part of the development can conclude with the Geiger tube actually mounted on the electroscope. And here it is, detecting pulses from background radiation. And this is quite lovely, since no complicated electronic apparatus is involved. 1, 2, 3, 4, 5, 6, 7. To avoid the tedium of counting individual pulses, an automatic counting device suggests itself. And so we're led to the scaler, which is no longer the black box that it might have been. And a whole series of further experiments now suggest themselves. Finally, we mustn't forget the need for some class experiments for our pupils to do themselves. A very simple detecting device is our old friend, the gold leaf electroscope. But this must be specially constructed so that it has a low capacity. The leaf must be thin, and it should be possible to replace the plate by this rod. It's charged like this. Simple, you see. With this low-capacity electroscope, class experiments can be done with a simple source inside here to illustrate principles. But for quantitative work, this instrument is recommended. This is a pocket dosimeter as used for safety purposes. The principle of it is the same as for a gold leaf electroscope, and is readily understood by the pupil. The gold leaf is replaced by a fine quartz fiber, which can be seen against the scale. This is the pocket dosimeter fixed into the ionization chamber, and this the electrode which extends into it. The perspex prism is merely to reflect light to illuminate the scale. The instrument can now be used for a variety of experiments. For example, absorption experiments with a source placed here. Even a quantitative measurement of the half-life of thoron is possible if we put the radioactive gas in the chamber. It's an instrument likely to be very important to us in school work. In this film, we've done no more than suggest ways in which the subject of radioactivity might be introduced, building from what the pupil already knows. Naturally, much more experimental work opens up once these introductory experiments have been done and understood.